continue.
Hello. Okay, this is the continuation of what I've been doing in the other video. Okay, I'm so sorry about that one, that the settings were not kind of like I had to look at the settings and then set up this one for more duration. Anyhow, that let's get back to where we stopped last time. So we drew this one. We drew this one. And then now we are looking for area entrap between these two curves. To get this done, what I'm gonna do, I can get this done by integrating along x-axis or y-axis. If I'm planning to integrate along x-axis, pretty much I have to get my operator dx. To get the operator dx, I really need to find a vertical strip. I'm going to focus on small strip, see? Strip, small strip. You see this strip? If I go down, this strip has a very small thickness called dx. See? I pick this one from y-axis at distance x. You see? At distance x. And this is, see, look at this. It looks like trapezoidal. It's not trapezoidal. This is infinitesimally small. Infinitesimally means extremely small. Small, rectangular, trapezoidal form, trapezoid, okay? But I'm going to get this since that these two ends are negligible, we can consider this one as a rectangular strip, vertical strip. Now we have a question of its height. I'm interested in this height. If this is x, from here to here, which is f of x, that's y. From here to here, g of x. If that's the case, this distance is nothing but f of x minus gx. On the other hand, I prefer to denote this also by y. Since it's on the top, I'm going to say y top. Y top is given by yt. This one, y bottom. Therefore, I can abbreviate that one by yb. So this is nothing but yt minus yb in another way. Look at, I got a vertical, infinitesimally small vertical strip of with dx and height f of x minus gx. And once you find the area of that small strip, that's more than enough for you to find the area of the whole region entrapped between f of x and gx over the interval 1 to 3. That area, in order to get that one, what's going to happen, once you are done with the area of this strip, you're going to stack these strips on top of each other, infinitely many, that strips on top of each other to cover the whole region. That the stacking of all these infinitely many rectangular vertical strip will be definitely taken care of mathematically by the integral. That's the beauty of math. And the beauty of math is this is one of the example. So beautiful. So let's write this one very clearly. I'm going to write something very clearly. Okay, I'm going to denote this by g of x, which is 4x minus x squared. Everything has been labeled. We have taken our area. We have chosen a small, infinitesimally small vertical strip of width dx and height that. So I'm going to write here clearly. Consider an infinitesimally small rectangular vertical strip of width dx and height or sometimes you can call the length or length of f of x minus gx, which is same as y t minus yb at distance x from the origin along the x-axis, or you can simply say O from the y-axis, from the y-axis. See, I'm going to consider an infinitesimally small rectangular vertical strip of with dx and height or length of f of x minus gx. This is yt minus yb at distance x. That's the general point. This is a general point. From the origin along the x-axis or from the y-axis. Okay. Then I'm going to take this small strip out and work on that. And later on, I'm going to stack the small strips on each other to cover the whole region. See? So its width is dx. Its height is f of x minus gx or yt minus yb, or we can plug in the values now. X squared minus 4x plus 10 minus 4x minus x squared. That is x squared minus 4x plus 10 minus 4x plus x squared. Then x squared, see, like terms, 2x squared. See? Then these two, minus 8x squared plus 10. See? That's the difference. That would be the difference. Plus 10. See, it's a small. Its area, I'm going to say this one, infinitesimally small area is given by dA. See, dA, not a dA. dA. Therefore, I can easily write, area, therefore, it means like I'm referring to the small vertical strip, therefore, its area is given by dA given by length or height times width. See, length and width. Then we can plug in length is nothing but 2x squared minus 8x plus 10. Width is nothing but dx. This is dA. See, that's the infinitesimally small area of that small strip. Now I'm interested in not the area of this strip. I really want to cover the whole region by stacking all these strips on top of each other from 1 to 3. Therefore, the total area, of the region between f of x and gx over the interval 1, 3 is, say what? I'm going to denote that by A. A is nothing but integral of dA. See? Integral of dA. It's nothing but dA, see, going from x equals 1 to x equals 3, x 2x squared minus 8x plus 10 dx. See, very small integral, but the setup is very heavy. Now let's integrate. I'm going to close this. I'm going to erase this one. See? So therefore A, this is what I'm going to. So let's integrate. 2x to the third divided by 3 minus 8x squared over 2 plus 10x. And you have to put the upper bound, which is x equals 1 and x equals 3. Plug in into this expression. So let's plug in into this one. 2 over 3 times x to the third means 3 to the third minus 8 divided by 2 is 4. 3 to the second plus 10 times 3. Close it. Negative minus lower bound. 2/3 1 to the third minus 4 times 1 to the second plus 10 times 1. Then this would be 1, 3 and 3 get cancelled over 3 to the second, which is 9. 9 times 2, 18 minus 3 to the second is 9. 9 times 4 is 36 plus 30 minus 2/3 minus 4 plus 10. See? Let's simplify further down. Then here minus 6, 18 minus 6 is 12. 12 minus 2/3 is 1, 10 minus 4 is 6, negative 6. Then 12 minus 6 is 6, 6 minus 2/3. Then common denominator, least common denominator, 3, 3 times 6, 18, minus 2, 16 over 3 square units. Square unit. That's the total area of the region entrapped between f of x and g of x. Thank you very much for watching this video, and I'm going to get back to with more problems, more solutions down the road. Until then, tata, bye bye.